Let's start from analyzing how change the way the users actually interact with our software programs. Once upon a time, actually not so long ago, because at least in Italy, some larger enterprise still using this kind of system, we have the command line interface. Each interaction with the software were done using commands. And this actually working, but it was a problem because the initial barrier to actually use the software program is really high. The users must know exactly the commands available inside the system, how they can be used, the arcs to use them, and how they behave when they are actually used. Then we move to graphical user interface. This is not a case I used Amazon because I love the buying experience of Amazon, but for me, at least for me, it's a nightmare when you move to side menus like the user preferences or something like that. This actually democratized the use of software. It's much easier to use something visual than the command line interface, but we still have some space to improve the user experience of our customers. This is actually the next big thing happening in our industry, the conversational interfaces. This is a screenshot from a POC I did a couple of months ago for one customer. And this is a personal shopping assistant. I don't know if you can read from the last seats, but basically, I'm asking him, okay, I would like to buy this kind of dress, just describing it in natural language, and they have enough information to give me the product that I can buy. And why this is important for us? Because name a better interaction than just asking what you need without filling forms, without running commands, or without checkbox around a web page. This is actually what happens when you go to a physical store to buy something. The store employees don't ask you to fill forms, fill values into drop-downs, and so on. You just ask in your natural language what you are looking for, and they have enough information to answer to your question. But like every revolution, the foundation is important. And every command, every forms, every prompts you can send to a system, doesn't matter if it is a CLI, a graphical user interface, or an AI agent, at the end, everything can be reduced to APIs. And the most important things are how you can access the data that are presented to the users. It's all about API and data. But what is the big difference between, okay, leave the CLI now, just talking about graphical user interface and the conversational interfaces. What's the difference? The difference and the big challenge too lies in how the behavior of the system is managed. When you are working in a traditional system, let me say, you define your APIs, and all the workflow that define how the APIs are called is triggered and managed using code, is managed programmatically. You write your APIs, and each interaction between APIs and graphical user interface is defined using imperative or declarative programming language. Using AI agents and providing conversational interfaces, first, the input is not well-defined, is not structured. You are asking a question in natural language, so even if the meaning of the prompt could be the same, the structure can be different. And also, all the workflow behind the decision-taking of the agent is actually managed by a single intelligent entity. It's not defined by programmatically data structures, but is described by using natural language. What does it mean? Let's do an example. During the presentation, we are going to use always the example of an e-commerce, not because I'm developing e-commerce, but because it's simple to understand. Let's try, for example, to see what happened when you do checkout on an e-commerce. You click the button checkout, you call the save cart route, the cart service do something, then check the stock to see if the products you want to buy are available, then place the order and create the receipts. Everything is defined using code, and everything can be always the same. If I do a checkout and another one 1 year after do the same action, the flow is the same. Okay, we could have a tree of possibilities, but are always defined, are always the same. With the AI agents is different because I send the prompt to the agent, and then there is a reasoning and orchestration process that decide actually what is the flow the agent will take to provide an answer. The agent is provided with several tools, the same we had in the normal structure, but the decision making is up to the agent. We can't actually write code to define the agents, it's just described. So now, let's define what an agent actually is. This is a picture taken from the AI agent paper made by Google 1 year ago. We have three main components. The first one is the model, of course, Gemini, GPT, and we will see later we also have many other alternatives to this bigger model. The orchestration layer, where all the decision making is managed, and the tools. The tools are the functions we provide to the agents. The tools are the hands of the agent that connect the model, the agent reasoning with the real-world systems. Let's analyze all these three components. First, models. Why a model is different from an agent? This is another table taken from the same paper. The main two reasons are basically two. The first one is the native tool implementation. Agents are born to be integrated with tool to interact with the external system, with the real world. Models out of the box can't actually get real-time data or perform action outside the neural network boundaries. Second is the reasoning. I'm not talking about the reasoning inside the model, but the decision-making the agent takes. There are a lot of prompt engineering techniques. We will see later how we can use them to orchestrating the agent actions, but we can use these techniques to write prompts for the model, but this is not a primary implementation for that. It's more important to use prompt engineering techniques to actually let the agent work as we expect. Second, as we don't need to be Einstein to sum two numbers together, models, we don't need bigger models like Gemini or GPT to do simple tasks. There are not only LLMs, but we also have small language models. Here you can see some example, Phi3 from Microsoft, Llama 3 8B from Meta, and Gemma from Google. They differ for many different reasons, and all of them are related to the reasoning capabilities of the model. For example, the number of parameters is directly related to the pattern complexity that the neural network can actually understand. The token complexity is related to the words nuance that the model can understand, can return. But what is important to know for us is that both of them have some pros and cons. First, large language models are bigger, as the name suggests. So the resources needed to run large language model are very, very high. You need bigger GPUs to run, for example, a Quen model, for example, remaining in the open source space. So this is directly impact your operational cost. And then, but the pros are that these models are more general purpose, and because are trained on larger training data, and can do more complex tasks. On the other hand, small language models allow us to easily fine-tune the model for specific tasks, and because they can handle tasks with a lower complexity and are cheaper to run and manage on self-hosted infrastructure, for example. Orchestration. What happens when you ask something to the agent? First, you send a user prompt. The agent takes the user prompt and start the reasoning orchestration layer. The orchestration layer is managed by the instruction prompt. It's something you provide once to the agent, and they keep it for all its life. What happened? First, the agent understands the request, the user prompt, decompose this request in smaller tasks to be managed, and then plan the action to take to give actually the answer to the user. Since the agent will use tools, and tools have parameters to be used, of course, extract the data they need to from the user prompts or from other tools to actually call the tools he planned to use, parse the response from the tools, and return a result. So, how can we actually write this instruction prompt to be actually trustable in the results that the agent will return? There are many different prompt engineering techniques. The most known are basically two: the COT, chain of thought, and the TOT, which is actually an evolution of COT, that means free of thoughts. It's basically basically the COT in a larger scale. How does they work? Basically, COT is instructing the agent doing examples. You will do to the agent examples of prompts and answer that allow the agent to reason and find patterns within this example to perform its actions during the execution. Tools. We have tools, but we don't need to programmatically say to the agent how they use it. He will understand which is the best tool, how to call the tool from the description you add to the function you provide to the tool. We have two different ways to provide tools to the agent. The first one is custom tools for a single agent. Write your Python function inside the agent. And the second one is MCP tool. We talked a lot today about MCP. It can be delivered by using Docker images, or for example, this is a screenshot from an ADK agent development kit agent. You can use also an npx, so node packages to add MCP tools. I can communicate using standard input-output or HTTP protocols. So, if we want to provide a conversational interface to our product, what could be a good roadmap, for example? First, we have the e-commerce front-end. The APIs we can define the APIs in CRUD, so APIs related to a specific entity that perform action like creating, editing, deleting, or getting a specific entity, and action that define more complex workflows. The best way to start is start simple. Start with a easy single prompt, single agent architecture, and write your tools right inside the agent, and move it in a separate touch point. Don't waste time to integrate it into the front end. Then, things make complex, so move the tools into an MCP. This makes it easier to share the tools between different agents, because in the next step we will see that the agent architecture will be distributed, and start to move some actions that are programmatically defined to delegating them to the agent orchestration. For example, in the first place, we could have a place refund API that performs the entire refund process. But we can delegate all the steps that the refund process do programmatically to the agent reasoning. So we can just provide a get or post routes for refunds and order and let the agent with the reasoning process to understand that first he needs to check the order status, then create a new refund and then update the order. At the end of the day, what you need to give to the agent, it is the access to the data. Last, decouple by domains your agent. We started with a single agent architecture, and then we are moving to a distributed architecture where we have an orchestrating agent, which is the single entry point and proxy to specified agent for the catalog agent, invoicing agent, and stock agent. Now, the life is easier when we have to deal with modern touch points, modern backend services, but we often need to deal with legacy systems. How we can bring the data from legacy systems to the agent. This is a reference architecture, really simple reference architecture of the Digital Integration Hub. Gartner mentioned the Digital Integration Hub many times in their last reports. Basically, very quickly, we are going to take the data from the legacy system using a CDC, change data capture. There are a lot of open source alternatives like the Bayesium, for example. The CDC send each changes from the data to somewhere. It's basically an event-driven architecture, so it's a queue. A projection store is a service. Take these changes and store all the data into a projection storage, which is actually a copy of the data from the legacy system into an higher performance storage. And then we have an aggregation service that aggregate the data and a CRUD service that expose this data to the agent. Basically, we took the data without taking the computational layer of the legacy system to let modern touchpoint, not just agents, to access this data. And all happens in near real time, more or less. Before closing the presentation, some real-world topics that is worth mentioning. First, architectures. It's easier to do a single agent architecture. You have one agent, but you can have many tools with many different integration layers and many patterns to do this single agent architecture. But there are also many patterns for multi-agent architecture. On these slides, you will see the links. So there is a very good starting point to start understanding better what does it mean to make multi-agent architecture. Second, self-hosted or LLM as a service. In Europe, there is a bigger topic, which is the data sovereignty. Using LLM like Gemini or GPT, expose our data to this service provider. So, open question is better under data management and cost point of view to manage a smaller model in our infrastructure or to buy these tokens from these cloud providers. Last but not least, as for normal programming language, we have the unit test, integration test, and many more. Also, the output from the LLMs must be validated. And we have many different ways to do this evaluator. The first one, the most common one, is the human in the loop, where the human give a feedback about the answer we'll get from the agent or the LLM, or functions. You basically write function to compare the answer with a data set of must-known answers. And the last one, probably the most interesting one, is LLM as judge, where you are using actually an LLM to evaluate the output of another LLM. It's interesting to read this paper because it's explained how they handle the biases about this, this approach. The presentation is finished. Here is the QR code for my LinkedIn account if you want to add me on your network. I won't be able to do the Q&A later, so if you want to have a conversation or want to ask questions, ask me on LinkedIn or just stop me in the hallway or during the breaks. Thank you so much.